Take any positive integer and ask, how many primes are there below it? Mathematicians call this function pi of x. It's a staircase, flat stretches where nothing is prime, then a sudden step at every prime number. For small numbers, you just count. Pi of 10 is 4, the primes 2, 3, 5, and 7. Pi of 100 is 25. Pi of 1000, 168. You check each number, test whether it's prime, and move on. A computer can handle 1,000,000 in under a second. But the staircase doesn't stop. In 2022, Baugh and Kim Walisch computed pi of 10 to the 29th power, the exact count of every prime below a 1, followed by 29 zeros. The answer has 28 digits, over 1 billion primes. They didn't check each number, at 1 billion tests per second. That would take longer than the age of the universe. They used an algorithm that counts primes without ever looking at most of them. By the end of this video, you'll understand how it works. The oldest prime counting method is the sieve of Eratosthenes. Write out the numbers from 2 to n. Cross out every multiple of 2, then every multiple of 3, then 5, then 7. Whatever survives is prime. Count the survivors, and you have pi of n. For 100 numbers, this takes 100 steps. For 1,000,000 steps. The runtime grows in direct proportion to n. That's fine for small values, but for 10 to the 29th, you'd need to touch 10 to the 29th numbers. No machine on Earth can do that. And this isn't a limitation of the sieve, it's a limitation of any method that processes numbers one by one. If your algorithm visits each integer up to n, its runtime is at least proportional to n. To count primes below 10 to the 29th, you need an approach that skips almost everything. An approach that can somehow jump past vast stretches of the number line without touching them. You need a way to count without listing. In 1830, Legendre defined a function that makes this possible. Phi of x, a counts how many integers from 1 to x survive after you remove all multiples of the first a primes. Here is a concrete example. Take x equals 30 and sieve by the first 3 primes, 2, 3, and 5. Start with all 30 numbers. Remove every multiple of 2, that's 4, 6, 8, all the way to 30. 15 numbers gone. Now remove multiples of 3 that haven't already been crossed out. Then multiples of 5. 8 numbers survive. 1, 7, 11, 13, 17, 19, 23, and 29. So phi of 30, 3 equals 8. Notice what just happened. We ran a sieve on only 30 numbers, but the count we got tells us something about the primes in that range. 7 of those 8 survivors are prime. The only imposter is the number 1. Now here's the key observation. If you sieve out all primes up to the square root of x, then any survivor bigger than the square root of x must be prime. It can't be composite. A composite number always has a factor no larger than its own square root, and we've already removed all of those. The survivors above the square root are exactly the primes above the square root. This gives Legendre's identity. Pi of x equals phi of x, a plus a minus 1. The first term counts primes above the square root. The second adds back the small primes we used for sieving. The minus 1 removes the number 1, which survives every sieve but isn't prime. This is powerful. The entire problem of counting primes reduces to computing a single function, phi. But computing phi directly through inclusion-exclusion requires summing over every subset of the first a primes. That's 2 to the a terms, worse than the sieve itself. There's a better way. Phi satisfies a recursion. Phi of x, a equals phi of x, a minus 1, minus phi of x over p a say, a minus 1. Take the survivors after sieving by the first a minus 1 primes, and subtract those divisible by the 8th prime. Each call spawns 2 more, a binary tree of computation. To use Legendre's identity directly, you'd compute phi of x, pi of root x. For x equals 10 to the 29th, that means sieving by about 3 trillion primes. The recursion tree would have trillions of levels. Completely impractical. Ernst Meisel, in 1870, found a way to shrink this dramatically. Instead of sieving by all primes up to the square root, sieve only by primes up to the cube root of x. This is a much smaller set, but it leaves some composite survivors. The question is, how many. Any composite survivor must have all its prime factors larger than the cube root. If it had 3 such factors, their product would exceed x, which is impossible since the number is at most x. So every composite survivor has at most 2 large prime factors. Call their count P2. This gives Lehmer's formula. Pi of x equals phi of x, a plus a minus 1 minus P2. Here a is pi of the cube root of x. P2 is tractable. For each prime p between the cube root and the square root of x, you need to count how many primes q exist such that p times q is at most x. In other words, how many primes are there below x over p? That's just pi of x over p minus the primes you've already accounted for. Sum this over all primes p in the range, and you have P2. The number of terms is roughly the square root of x divided by its logarithm. Each term is a smaller value of pi, computable by the same method applied recursively. The work for P2 is manageable. The bottleneck is still phi. The recursion tree now has only a equals pi of x to the 1/3 levels, around 400,000 instead of 3 trillion, a massive improvement. But the tree still has an enormous number of leaves. Let's trace the recursion tree for a small example. Computing phi of 30,3. The first split gives phi of 30,2 minus phi of 6,2. Phi of 30,2 splits into phi of 30,1 minus phi of 10,1. Phi of 30,1 becomes phi of 30,0 minus phi of 15,0, which is just 30 minus 15, equals 15. You can see the pattern. Each call splits into 2, and the tree branches rapidly. The leaves at the bottom are of 2 types. Ordinary leaves reach a equals 0, where phi of any number, 0, is just the floor of that number, a trivial computation. Special leaves occur when the argument drops below the current prime, giving a small lookup value. For x equals 30, the tree has about a dozen leaves, no problem, but the tree grows fast. For x equals 10 to the 13, there are hundreds of millions of ordinary leaves. For 10 to the 23rd, the number reaches into the trillions. For 10 to the 29th, the tree has more leaves than any computer can visit one by one. Each leaf is trivially cheap to evaluate, it's just a floor function. But the sheer number of them is the bottleneck. The formula is exact, computing it is the problem. This is where prime counting was stuck for over a century. Meisel in 1870, Lehmer in 1959, they had the formula, but computing it for truly large x meant traversing an enormous tree of recursive calls. The identity was known. The bottleneck was evaluating it. What if you didn't have to visit each leaf individually? In 1985, Jeffrey Lagarias, Victor Miller, and Andrew Odlyzko asked a different question. Every ordinary leaf contributes a floor value, x divided by some product of primes. Instead of following the recursion tree down to each leaf one by one, what if you could collect all these contributions at once? Their insight was to use a sieve, not to find primes, but to accumulate the phi function in bulk. Take the interval from 1 to x to the 2/3, break it into manageable blocks. For each block, initialize a running count of all numbers in that range. Then for the first prime p1, subtract the count of its multiples in the block. What remains is the count of numbers not divisible by p1, which is exactly phi of that block, 1. Now sieve by p2. Subtract multiples of p2 that haven't already been removed. The updated count is phi of that block, 2. Continue through all a primes. Each subtraction step is exactly what one layer of the recursion tree would compute. But instead of doing it for one value of x at a time, you're doing it for an entire block simultaneously. At each sieving step, you're computing phi for thousands of arguments at once. The ordinary leaves that the recursion tree would have visited one by one are now collected in a single sweep through the sieve. The special leaves require individual handling, but there are far fewer of them, roughly x to the 1/3, and each takes constant work, total time proportional to x to the 2/3. For 10 to the 29th, that's about 10 to the 19th operations, organized into cache-friendly blocks that modern hardware can process efficiently. Delaglys and Riva refined the constant factors in 1996, and Kim Walisch's implementation pushed it further. This is the Lagarias, Miller-Odlyzko algorithm. Every record-breaking prime count since 1985, every single one, descends from this idea. The recursion tree, with its billions of individual leaves, is replaced by a single sieve sweep that collects them all at once. The bottleneck that stopped Meisel and Lehmer for over a century dissolved in one conceptual shift. Here is what the algorithm has made possible. Pi of 10 to the 13th, 346 billion primes, computed in seconds. Pi of 10 to the 23rd, a number with 21 digits, done in hours. Pi of 10 to the 29th, the current record, a 28-digit answer beginning 1520698, computed over several months on a distributed cluster. The algorithm, a direct descendant of LMO. Every one of these computations would be impossible with a sieve. The sieve touches every number up to x. LMO touches only about x to the 2/3 of them. And for x equals 10 to the 29th, that's the difference between 3 trillion years and a few months. The staircase of pi of x has been climbed higher than any naive method could ever reach, not by checking each step, but by finding a way to count the steps in bulk. No one will ever list every prime below 10 to the 29th, but thanks to 3 mathematicians in 1985, we know exactly how many there are.